Hi, everybody. This is Andy from Swarm64, and I want to thank you all for joining us today to learn about new scaling options for Postgres to help you with data warehousing and other applications. Presenting today, you're going to hear mainly from Jana Krosteva, who's Swarm's VP of Product and Innovation, and also Sebastian Dressler, who's Swarm's Head of Solution Architecture. And without further ado, let me turn it over to Jana. Jana?
Yeah, thank you, Andy. So hello, everybody, and welcome to our webinar. And today we are going to talk about how to first scale in and then do the scale out, and proposing new database scaling options with FPGAs. And I would really like to start this presentation by sharing a quote I really like, and I think it's directly related to what we are going to talk about today. It is from Saint-Exupéry, and it says like this: perfection is not reached when there is nothing left to add, but when there is nothing left to take away. And if we bring that quote into the subject matter of today's webinar, I believe it should sound something like this. In the big era of big data, perfection is not reached when there is nothing else to be added to the system, but when you have found a way to keep complexity low. But now let's start from the beginning, and let's first define what means complexity in this context. And yeah, just let me go back one slide. And when we talk about big data, actually we talk about huge amount of data that are produced, and that is the V from volume. We talk about high speed with which the data is generated, analyzed, and processed, and that is the V from velocity. We also have to talk about the V from the high diversity of data types and data sources, and that is the V from variety. Now let me go back and dig a little bit more into the V from velocity. Velocity is the key to be able to handle one of the most important things in your business, and that is the frequency of decision making. Being able to sustain a high frequency in decision making allows you to make small and possibly even automated adjustments of your decisions, and by that reduce the costs and also mitigate the risk. But velocity does not give you a sense of how good are the decisions you are taking. These come from the two additional V's of value and veracity that don't belong to the original definition of big data that is given by Gartner, and you can see here on the slides in the bottom part. So these two additional V's, the first one that is veracity, it comes from the truthworthiness of the data. And the last V, the V of value, actually is the one that makes your business move forward. Having access to all this enormous amount of data is completely useless unless you are able to turn that data into business value. Now, that's why these two additional V's are the ones that give you the perception whether or not your decisions are good. Now, let's think about a little bit about this definition of complexity into the big data domain. And now let's translate it into what happens to the system that is behind that have to cope up with all these requirements. So how does your data management solution looks like today? This complexity, of course, in the business gets translated into the complexity into the data management side. And what happens is that in many cases, you end up with different silos of data in specialized clusters. Then you will have a cluster for ingests, a different cluster for streaming analytics, a cluster for databases operations, and another one for your deep analytics, your NoSQL store, your Hadoop cluster, and so on and so forth. And then you would like to have some of this veracity and security on top with encryption and all that comes with the data maintenance. So with all this picture, actually what we want to discuss today is to bring to the table one possibility to contribute to keeping complexity low. And that's why it's the subject matter of today, that is scaling first and then scale out. And how we achieve that? So our product that is called Swarm64 Data Accelerator, Swarm64DA, is based on two pillars. The first one is open source Postgres, and the second one is acceleration. Now, open source and enterprise, that's something that might not match, at least historically. But what we have been seeing lately is that open source, that enterprise adapters are gradually shifting for being reluctant to accepting open source software to actually start actively demanding open source. And why this shift happens? It happens because open source solutions, even when provided by commercial vendors, help to prevent vendor locking and inhibit the overall software licensing costs. So this is very positive, and actually Postgres is a future-rich and an industry-proven database, but that will not be enough to handle all the complexity we have already talked about. And this is where our second pillar goes into action, and that is the acceleration. And we do that with programmable hardware and parallelized software. And we are going to talk about in detail about that today. And we are going to do that by telling you a story with two actors. And the actors of this story are myself, playing Yana Krasteva, playing as the analyst. And actually, my job is to solve business problems by learning from data, and by that, help businesses make better decisions using valuable information. I'm mostly interested on the V's of veracity and value. And what I really need is to be able to ask more questions and even more complicated questions to the database system in order to make accurate business decisions. And my partner today is
Sebastian, and I'm acting as the database administrator, and then my tasks are to install and configure databases, obviously, and also to monitor their performance and to do capacity planning. And in the terms of the big V's, I care most about the volume that hits the database and the speed on this volume, because my task is it to keep the database running under any circumstances. Now, in the webinar, we will show you some details around certain database setups, and for that we have a certain environment set up here. And in order to assess the performance of that setup, we will use benchmarks, obviously. And one of those benchmarks is the TPCH data warehouse benchmark, which is a standardized one and consists of 22 queries targeting 8 tables in the star schema. And I can actually scale this benchmark up to petabytes of data. And moreover, I can simulate single usage and also multiple users of the system. Now, we are of course aware that there is also TPCDS, which is more recent than TPCH, but it does not have so many official data points which we can compare to, and hence we opted for TPCH in that case. Now, talking about the setup in detail, we are using standard x86 hardware throughout the webinar, and based on that, we deployed a CentOS in the latest version of iteration 7, and on top of that, Postgres 11 and our Swarm 6040A version 2. And the benchmark we are going to use is, as said, the TPCH, in our case of 1 terabyte of data, and we are talking about 6 and 1.5 billion rows on the biggest tables here. Now, as said, we will show you certain configurations. We will start with single node setups and then look how it behaves with different cluster solutions and also our hardware acceleration. Now, to start straight away, we will look into Postgres for analytics in general. And Jana already said it, Postgres itself is one of the most trusted and powerful databases out there. And it is a very mature product. So, and as such, it's very respected for OLTP workloads, and that's more the common use of Postgres. However, it is also capable of running HTAP and other workloads, and in those analytical workloads we are mostly interested in today. Now, the question arises how to tune Postgres for analytics, and the most two common options are to obviously add indices to your data, which helps the database to do faster lookups. But those indices, they come at a cost, and that cost is extra CPU and storage. And also, talking about storage, it can happen that you get some suboptimal I/O patterns, which we refer to as scatter-gather. And also, the moment you use indices, you have to decide, do I want to have fast reads where the indices are for, or do I want to have fast writes? Which are typically slower, because the moment the data hits the database, the index needs to be updated, and that can take a while depending on the size on the index and how it is built. Now, another very common option is to add partitions. This is a bit similar to indices because you can improve the data lookup, because the database knows in which partition the data exists and can access that partition in a more direct manner. And also, you get a better maintenance here because you can simply remove partitions and add them. However, the downside is that there is some limitation in parallelism typically with Postgres. And on the other hand, you also have a hard time to change your partition schema. So if you decide that you want to change something in your complete schema, that might result in a complete resetup of your database. Now, let's look a bit into what Postgres within a single node configuration can do for us for a analytics query. And we do have a setup here with a single node, which is marked here as coordinator. And the following video will show you how we add users to the system, and those users, they run a single query, which is the TPCH query number 6. We will look into this query later a bit more detail so that we share the contents of the query and share the understanding about this. And we will just start a video now to see what happens. So you can see here that we started one user, we added one user to the system, and then we have here some nice graphs, and this is actually depicting the CPU usage on that single node. So it's at roughly 25% at the moment, and we speeded up the video a bit, and you see the query time returns in roughly 650 seconds. Now, what will happen if we add a second query to that? We just did so. So you see this second little user here. He runs at the same time next to the existing one already. And there's again a bit of speed up here because it takes quite a bit. And jumped suddenly from 600 seconds to 800 seconds, from 650 to 850 to be precise. And the second query also returned in roughly that same time. Now, what does this tell us? First, the query took longer because there was more load on the coordinator. And that could result from a resource bottleneck, which we would potentially need to analyze. On the other hand, the second query returned in almost the same time, which is good because it gives you some form of scalability. Now, as said, this is a pure benchmark point of view. And the more interesting thing for the analyst actually is that she wants to run her query and see how fast her query is. And for that, I'm handing over to Jana again.
So I'm a data analyst, and I actually care about real world and asking my real world questions. So although my DBA has told me that the database is working well enough because he has run all his benchmarks, I actually insist on running something from the real world. And for that, in this case, I have chosen the New York taxi driver dataset. This is a well-known several billions of rows dataset, in which one you can ask questions like what kind of locations people have been pick up from, where they have been dropped off, how much tip they have given, and what's the fare of the taxi. And the question I will want to ask this time is, how much more generous are passengers being picked up at a certain point compared to those being dropped off at the same point? And the point I have selected here is a bar in New York City that is the favorite bar of one former colleague of ours. And yeah, basically, in simple words, I want to know if having a couple of drinks make people give better tips. And here now on the right side, you can see the query, and it has some kind of, it's not, let's say it's not the simplest one that can be. There is a join, and yeah, we have some filtering here and there, and we can run now the query. And I want first to see the results, and it will be in percentage. Now I know that 47% is the tipping higher when people get picked up compared to when people get drop off. And this query returned in 1 minute, 56 seconds. It has run from call, so the cache was cleaned up before. And we can see that the result, I will say, is not that bad, but I will then stop digging for more insights here. So I will not be able to ask further and more complicated questions, something that to run my business is something that I would like to do in general. So I will talk with my colleague.
So, and from me, that is something that is not so nice to happen, because having an unhappy user is not something nice for a DBA. And to resolve that issue now, we will look into the queries and we will just see what happened actually. And we start again with the TPCH, with the benchmark query. And as you can see, this is a rather straightforward thing. It consists of a part that does scanning. And now I'm thinking by myself, if I could add more parallelism to that scan part, then it would return much faster suddenly. Why? Because I can use much more I/O from the I/O subsystem. But I'm also aware that I might have indices put on the table in order to find the data faster. And those indices might cause me the scatter-gather we talked about earlier, meaning that the database has to point to blocks which are not necessarily in a contiguous range to be fetched. Moreover, I'm aware that we can have statistics in Postgres, which actually help to improve the selectivity. And if my statistics are well enough, if my data is well enough in the system and well enough analyzed, then this will help the performance. Now, if we look into the query Jana wrote and Jana sent to the system, it's a bit different. So we have a join here, as she mentioned. We are again aware that this join might do a scatter-gather pattern because the data might not be ingested in the order as it is requested here. But on the other hand, there's also some scanning again. So here again, parallelism could help if I could put it enough down to the I/O, and also we are having indices which help to reduce the data volume. Now the interesting thing here is that because we have a cross join, and due to the behavior of Postgres, it might happen that these two query parts, although they are almost identical, that they are executed in sequence. Maybe they're executed in parallel and then joined together, but judging from the performance we've seen, it's rather a sequential execution here. So the big question is, how do I handle this? Also keeping in mind that this data set might grow more larger and might grow beyond 1 billion rows or more multiple than that, like 10 billion rows or whatever. So, well, the obvious solution for me would be to just scale out that system. So I just go ahead and I throw more hardware at it. Now, before I'm going to jump into buying more hardware, I'm thinking about the case and I'm trying to think about why I would do this and when I would do this. Now, the typical reason to do a scale out is you want to separate concerns. So you want to split your workload into the two parts you're having. One is I/O intensive, like the scanning, and one is CPU intensive, like the finalization of the query, meaning the number crunching that needs to be on the CPU. And by separating those two, I can adjust my nodes to their use case. So I can have very I/O capable nodes for the data, and I can have CPU nodes or nodes with high amount of CPU resources for my number crunching. And a typical scale-up approach, therefore, is to split into a coordinator node, which has no data on, but it has metadata on. So it does not have direct access to the data, but it knows how to get the data. And because it has a lot of CPU resources, it needs to do the compute intensive part. On the other hand, we have then data nodes where the actual data is on, and these nodes, they need to be made for I/O operations. And the interesting point is that we can actually achieve that with native Postgres tools, because as you may know, there's a Postgres foreign data wrapper, and with that foreign data wrapper, you can connect multiple Postgres instances with each other, and then you can query your tables as if it was on the very same node you are currently accessing, but in fact it goes to another node and fetches the data from there. So we can use this with dimension partitions to create a nice cluster without any third-party tools, but with Postgres tools only. However, there's a pitfall here, and that is that the Postgres foreign data wrapper is not parallelized out of the box. So if you would run a query on such a system with the provided Postgres foreign data wrapper, the query would be executed in sequence, and you would actually achieve the opposite, meaning you get much slower queries than with a single node. However, Swarm 64 has provided a patch, and I'm happily using that. And by having that patch in place, we can actually set up a system like depicted here. So what we have here is a relatively small cluster with one coordinator and two data nodes. And as mentioned, the data nodes, they host the data. The coordinator only has a schema and knows how to access the data. And we are going to run the exactly same query, TPCH query number 6 on this setup, and we just see what's going to happen if we do so. Now just let's run this query. So it's the same procedure as before. We add a user to the system and it just starts running. You see that there's actually the IO load ramping up here. So we're reading at 1 to 2 gigabyte per second. We speed it up again a bit. And you also see network traffic here. So because we need to obviously transfer the data from the nodes to the coordinator. And now this query is about to finish, and it took only 300 seconds. And this is a speed up of more than 3x here. Sorry, it's 2x. We had 600 seconds before. Now we are going to add a second user. And in the previous result, we were going up from 650 seconds to 850 seconds. So quite a jump. We're just going to see what's happening now with 2 queries running at the same time. We give it a little speed up again here with the video and should return in a moment. So now it's the time that it returns. Let's watch the numbers closely. It's 300 seconds, so that's only 20 seconds more than with 1 user. And you see the upper query also returns in almost the same time. Now we can add a second coordinator, and this is actually an elastic setup because there is no data on the coordinator, so we can just spawn up more and have a load balancer in front to distribute the load across the coordinators. And we have now 4 users on the system, and as you can see, the query times, they're actually stable. So from the DBA's point of view, this is a very nicely working, well-balanced system now. I got a nice speed up for my analyst, and I hope that she's happy now with her query and her performance. Let's have a look.
Okay, now let's see all this, how this all very nice setup behave in the real world. And I'm right now the single analyst accessing the system, running my same taxi driver datasets and my query. So I'm going now to run my query. Same one, same query, same result. Still 47% of the people tip more after some drinks. And my execution time is, okay. Yeah, now you see it's 1 minute 46 seconds. And as a reminder, this is 10 seconds less than the single node solution. So, okay, yeah, we have a nice system behind, but actually it's not giving me the possibility of asking more questions and having faster response. So what is the conclusion from my side? From my side, the conclusion is that in this case, the system has become more complex, and therefore it's more expensive to maintain, and you spend more time actually managing the data and managing the system than the value you can gain from it. So that's my conclusion. Now the question is, are there any other options? And here the options that Swarm we propose is to use programmable accelerators. These are, in a nutshell, PCI cards that have an FPGA on it, and that you can build dedicated hardware on top of these FPGAs. FPGAs in general are suitable for stream processing, and their particular characteristic is that they are reprogrammable, which means that they have extended life cycle, and the code you program for one FPGA is in its biggest part portable across different types of FPGA. So FPGAs actually are not a new technology. They have been there for a while. And the question is, why now we are talking about FPGA acceleration for databases? FPGAs lately are becoming mainstreams. We are seeing them being adopted in cloud environment, and also there are a variety of FPGA accelerators that has been certified for on-premises solutions. And what Swarm has made is that we have built a complete parallel query processing on the FPGA. But this is not enough to achieve the acceleration that we need. We need as well some parallelization on the software side.
Right, and as mentioned before, Postgres limits parallelism sometimes. Now, why is that? Because Postgres was mainly made for transactional workloads, and therefore limiting parallelism for you is a safety measure, because it should not happen that you lose any of your transactional data when you have a very highly loaded system, or to put it in other terms, if there are many users accessing the system, you want to serve them all in the best case and not have any unhappy user. Now, to bring that into the world of analytics, where you want to have a lot of parallelism, we did two main things. We first improved the data layout of the stored data, which is a concept we call optimized columns. We will dig into this in a moment. And secondly, there is workload management, which is capable of looking into the system usage and assigning resources to the query execution depending on the state of the system. So if I have a system which is currently not so loaded with few users, then those few users will get more resources. And the moment there are more users accessing the system, the resources are distributed equally amongst those again to guarantee a fair use of the database. Now, in terms of those optimized columns, we compare these to the traditional indices you know from Postgres. And you can think of a index in Postgres as a marking point for a block you need to fetch. So when you run a query, then essentially Postgres gets a list of blocks it needs to fetch to work on. And those blocks, they might be distributed all over your I/O system. So if you have SSDs, for instance, then they might be spread across those SSDs, and they need to be collected together first in most of the cases. Now, this leads to a lot of I/O requests and a latency that is compared rather high because you have n many requests. Now, with the optimized columns, we actually remove the need for indices and we change the data layout such that your I/O system is capable of doing a continuous transfer of data. So these blocks, they are reduced because we also use bigger blocks which is suited more for analytics. And by that, we reduce the amount of I/O requests you need to do. And by that, you can increase the throughput and effectively decrease the latency. Now, in combination with hardware acceleration, a complete query looks like the following. We generate first a parallel plan, and this is helped by changing the data layout and also particularly by rewriting some of the queries internally. So there is no need for the user to rewrite the query. The database or our extension in that case does this for you automatically. Then with the help of the optimized columns, we can generate a very high throughput to the I/O subsystem. Moreover, the data is compressed, and that is where the hardware comes into play because the decompression happens on the hardware. So there is no CPU overhead when you need to access your data in the first place. So the data is compressed, then we push down the select to actually reduce the columns we need, and the where statement is also pushed down to the card and applied to the data, so that at the end of this processing you get a first result which is mainly consisting of a very much reduced data set. This reduced data set is then given back to the CPU where the finalization of the query happens. So if you, for instance, do an aggregation like a sum over your data, over your rows, then this sum is at the moment calculated on the CPU. Now, how does this look in practice? We have here another video, which is this time showing a side-by-side comparison between Postgres and Swarm. And we will just run this again. So as you can see, I just paused the video a bit. We run the query number 6 from TPCH. Again, this is like a dual socket system. Each socket is allocated to one database. On the left-hand side, you see Swarm64DA, the accelerated Postgres, and on the right-hand side, you see a Postgres without acceleration. Now, when we run the query, what is noticeable is that we immediately ramp up the CPU usage here because we can push down more to the I/O subsystem, and you also see that the FPGA transfers data. In contrast to the Postgres side, where the CPU utilization is rather low because of the reduced parallelism, and we also have to read quite a lot from disk, which is reduced here on this side because the data is compressed. Now, if we continue, we can see that we actually finished within 14 seconds our query, and we'll just fast forward a bit to see what happens with Postgres. And here we can see that Postgres took 1400 seconds in that case. So this is 100x of speed up we achieve over Postgres, and also you can see the results are matching. Now, I am able to provide my analyst a hardware accelerated single node, and I hope that she is happy now.
Okay, now let's see what this accelerated single node can do with my real world query. And I'm still looking for the same thing, that is to know if people eat more after having some drinks. And this time it took 30 seconds. So yeah, now I can ask a lot more questions, and I can start digging of what kind of people are these people, or what other places they like to go, and what's the biggest tip somebody can have. So in conclusion, for this part of the single node, based on the taxi data, we have seen that the single node with Postgres took 1 minute 56 seconds, and the single node with acceleration took 30 seconds, which means that our single node productivity increased 4 times. We got a big change in performance and lower complexity, because we will have need a quite scale out solution to actually achieve these 30 seconds if we didn't have the single node acceleration. And this actually allows us to postpone the scale out of the system. We can stay simple and keep it simple for longer time. And in the future, when we decide eventually to scale out, then if we have this of 4 times effectiveness factor, it means that we will have to maintain much less nodes. Maintaining 3-node cluster is always cheaper and easier than a 12-node cluster. And that's exactly what we are going to show next.
Right, so my analyst asked now to put in the hardware acceleration into the cluster setup we've seen before. And this actually turns out to be really easy, because all I need to do is get me the FPGA card and put it into the system, and that's it. I don't have to change any of the queries. All I need to do is to tell the system to use the data via the card, where it's then getting compressed and getting access directly. And that's why we had not to change anything of that setup. It's the very same setup as before, except that we are now going to use the hardware acceleration here. So I'm just going to start this. It's again the same mechanism. And as you can see, we run the first query of our TPCH query in 14 seconds. We have quite some increased load on the Ethernet, which we did not have before. And our data acceleration is actually doing its work. So the disk I/O at 1.8 to 2 gigabyte per second is directly provided to the hardware accelerator, where it's getting decompressed and filtered out and then prepared by the CPU. So what happens now if we're going to add more users? And again, this is expected. We see a slight increase in query time because the system gets more loaded, but at the same time, we doubled here the amount of data transfer through the network. You can see that the I/O is going down, which is because the data is compressed. So we can already use, we already have the data set completely in RAM, reducing the I/O. So if this was network attached I/O, then you would save bandwidth here, because you can hold the complete data set in RAM. And we can now just add many more users to the system, like 4. And as you can see, this is really stable. So we don't have a huge increase in query time. It increased by roughly 1 to 2 seconds, and they are all running in parallel. And we can do the very same as before. So we can add another coordinator node here, and then the load gets distributed over the coordinator nodes. As you can see, it halves again the network bandwidth here. So the other half goes here actually. And we, again, by that, we can reduce the load on the coordinators and get slightly better numbers here, meaning that with 2 coordinators in that system, we can drive even more users in the end. Now, let's have a last look into the query from Jana.
So now we are going to run for the last time the query. And this time it took 21 seconds for the accelerator scale out. So now let's gather some conclusions around the cluster. For the cluster scale out, we are taking here the information from the TPCH query 6 run. We saw that the performance of the standalone Postgres was 170 seconds, which gets reflected into approximately 5 queries per hour that can be run for a single user. And in the scale out, we had 283 seconds query return time. And then there the query per hours are 12 queries per hour per user. And in the accelerated version, we have 12 seconds return time and 235 queries per hour per user. So what we have achieved by adding Swarm64 Data Accelerator is that we have increased throughput, we have much more concurrency, and a system that performs much better. Now let's move on to the last slide of this webinar, and to have the overall conclusion. So our conclusion is that PostgreSQL is actually a great tool for analytics. It needs a bit of debug knowledge and some tuning, but it actually does the job very well. The single performance is acceptable, but you can have much more throughput and much more parallelism if you do scaling with Swarm64, the data accelerator. If you need more, there is a simple way to scale out Postgres with native resources, and you can simply download our open source patch for parallelization of the foreign data wrapper from our webpage. And if you need then more, you can add Swarm64 DA hardware acceleration to the cluster as well. So we have provided a solution to keep the system simple based on open source Postgres and Swarm64 data accelerator.